Hey everyone, Morgan here. So we're on page 11 of the Honors Chemistry Atoms and Light lectures, and we're going to be talking today about the Bohr model. So I have this kind of obtuse question here for you. What do beer, football, yes, I spelled that correctly, and the 1908 Olympics have to do with chemistry? Maybe that'll get your attention for a little while. Okay, so this is a picture of what we call a bright line spectrum. This is the bright line spectrum for hydrogen. And it is not a continuous spectrum. It's not one of those, Hello Kitty rainbows that I've been talking about. What we are seeing here is four distinct monochromatic lines. They have just one color. There's a red one, there's a blue-green, a blue-violet, and a violet. The wavelengths are listed there for you. They're on your outline. So when you take a tube containing hydrogen gas, and this is not terribly different than the tubes that are in the lights in the ceiling in the classroom, and you shine that light, focus it into a prism, rather than generating a continuous spectrum rainbow, we get these four colors. And this was something that was discovered in the mid-1800s, and it really had people puzzling about how it or why it happens. What causes this? Okay, so why does this happen? Okay, Johann Balmer. Balmer was a Swiss high school science teacher, and he was playing around with this and discovered doing graphing, and graphing's important, you know that, okay, that he could predict the wavelength of each of those lines. They fit an equation. It was a straight line equation. It was a y equals mx plus b equation. And this is what it looked like. Okay, 1 over the wavelength equal to constant, 109,680 centimeters to the minus 1, times 1/4 minus 1 over a number squared. And that value for that number n would be 3, 4, 5, and 6. It was 3 when it was the red light. It was 4 when it was the blue-green. It was 5 when it was the blue-violet. And it was 6 when it was the violet light. Now, he had no idea what this meant. He just knew it fit the data. Okay, so the mathematical reasoning is solid. Explaining the implication of n was not accomplished. Okay? Now, not long after Balmer, a university professor named Rydberg, looking at this, actually was able to take the idea one step farther. Balmer, being a high school teacher, only had the instrumentation to see stuff with his eyes. But Rydberg had more sophisticated equipment and could actually measure things outside the visible light spectrum, in the ultraviolet and in the infrared. Okay? So, he modified the equation. Instead of 1/4 minus 1 over n squared, he said that you would have 1 over n final squared minus 1 over n initial squared. And n final would always be a smaller number than n initial. And that n sub f is the n final, and that n sub I is the n initial. Now this actually allowed Rydberg to see a lot more lines. He looked at them with instrumentation. He now knew where to look based upon the equation, and he found a lot of lines, okay? Except he still did not know what the physical implication for n initial and n final was. Okay? All right, so let's make a table here. And we have, this is the next page in the outline, we have a set of lines that are called the Lyman series. N final is equal to the number 1. And n initial can be 2 or 3 or 4. And those lines fall in the UV region, the ultraviolet. Those are relatively high energy. Now, we already know about Balmer, and it turns out that n final for Balmer was 2, because 2 squared gives you 4, and that's where that 1/4 came from in his equation. The n initial would be 3, 4, 5, etc., like we showed before, and we already said this is in the visible light part of the spectrum. Now, Paschen, another spectroscopist, all of these sets of lines were named for different spectroscopists who were working on this, but Paschen identified a set where n final would equal 3, n initial would have to be bigger, so 4, 5, or 6, and that was in the near IR. And what that means is, since the IR is such a big part of the spectrum, this is the area that's near the visible light portion of the spectrum. A guy named Brackett, n final of 4, n initial 5, 6, 7, in the middle of the IR. And I got to tell you, my OCD is really happy right now because I'm seeing pattern to all of this. Now, the best name set, this is actually named for a guy named Fund, okay? And it follows exactly what you think it should, okay? And it goes all the way out into the far IR. Now, could they explain what any of this meant? No. They just knew that these numbers fit, and they predicted the lines, but no idea about what n final meant or n initial meant. Okay, well, let's go back. Let's do some reviewing. Let's talk about J.J. Thompson again. J.J. Thompson gave us what we call the plum pudding model for the structure of the atom. And this is what a plum pudding would look like. It's a British dessert, okay? And this one happens to be covered with some cream, although what you can't tell from the pictures, they're usually soaked in brandy or rum, okay? And this is a traditional Christmas dessert, okay? Now, in the plum pudding model, the atom was a hard, dense sphere. And all of those little pieces of fruit that are in there, okay, those represented the electrons. The negative electrons were the plum part, although we'd probably call it raisin in America. The positive part was the pudding itself, the cake, okay? And it looked something like this, even distribution of positive and negative charge. Now, Rutherford gave us our next picture here of the atom. And Rutherford, if you remember, told us that the atom was mostly empty space because alpha particles could fly through thin gold foil. A certain number of them would be deflected, and then a very tiny fraction of them, about 1 out of every 20,000, would bounce back. It would just hit something and cause it to bounce back. That something has to be very dense, and it has to be positively charged. Because remember, alpha particles have positive charge also. And it has to be dense and massive so the thing bounces off. Okay? It's a great stamp that actually shows this happening. It's from New Zealand. Rutherford was from New Zealand. He was a Kiwi. Now, this was originally referred to in Rutherford's work as a planetary model. He thought that this would kind of approximate what our solar system looked like, with a nucleus that's tiny, positively charged, and very massive, and electrons that circled it like planets circle the sun. Okay. There were some other people at about the same time starting to come up with similar ideas, but they're not really well known in the chemistry textbooks. Okay, now, here's a weird story. In 1911, there's a guy named Niels Bohr. Now, Niels Bohr was working as a postdoc in J.J. Thompson's lab. Bohr was from Denmark, specifically Copenhagen. Both his parents were professors. Tons of privilege, white guy, you get the picture here, okay? And he was working for Thompson, and he and Thompson were not seen eye to eye. And that was weighing heavily on Bohr. In fact, he was ready to quit. He had a 2-year postdoc. He'd gone through about a year and a half of it, and he was just going to pack up and head back to Copenhagen. Now, the night before he was going to leave, there was a party. Maybe we would use the term class reunion, a gathering of lots of people who had worked for J.J. Thompson. And remember that Rutherford had been one of his students. And at this point, Rutherford had left Canada. He'd come back to Britain. He was up in Manchester. Okay. And Manchester, that's a pretty rough industrial area. Not a whole lot of people going to the university, but big fans of soccer. Manchester United. Okay. Now, Rutherford saw Bohr and screamed from across the room, "I know you. I saw you play football for the team from Denmark at the 1908 Olympics, which were in London." And Bohr kind of smiled and went over to him and says, "No, actually, it wasn't me. It was my older brother, Harold. I wasn't good enough to make the team," et cetera, et cetera. But they started to talk a lot. And Rutherford exposed Bohr to something that Thompson was not thinking about, and that was this planetary model. And Bohr was sold. Instead of going back to Copenhagen, he ended up going up to Manchester and spending the rest of his postdoc working for Ernest Rutherford. Red Devils. I think that's the mascot for Manchester United. Okay. Now, when Bohr returned to Denmark, because of all of his connections, he was actually able to set up his own lab, much like J.J. Thompson, much like Rutherford. And he was actually given financial support from industry. You see, today, if you're doing research in physics like this, you're going to be supported by the government. National Science Foundation, Department of Energy, Department of Defense, something like that. Back then, all research was sponsored by industry. And the big industry in Copenhagen is breweries. So Bohr's money for his research came from the Carlsberg Brewery. So what we have here is just this stroke of luck that beer, football, and the 1908 Olympics made these next discoveries possible. Now, this is a stamp from Denmark featuring Bohr. Great stamp, okay? Now, Bohr, while setting up the lab, was interviewing former students and showing them this planetary model. And one of them asked him, could this be used to actually explain the Balmer formula? And Bohr was unfamiliar with it. So they went to the library, they looked it up, and I've heard a lot of different versions of this story. But they basically come down to the nutshell that Bohr went home or went to his office, went to the library, and in the next 24 hours pounded out his whole theory of the atom, and it matched the data. He said that those orbits that the electron traveled in were very well-defined circular orbits. And if they're numbered from the inside out, concentric circles, those numbers correspond to the values of n in those equations, both Balmer and Rydberg. Okay? And electrons jump or transition between those orbits. And when they drop from a higher energy orbit to a lower energy orbit, energy is released. And they always release the same amount of energy depending upon the distance that they drop. And that's why you get the bright line spectrum. It's not a continuous flow of energy. It's very specific, well-defined amounts. So this is kind of what it would look like. Not as circle. I mean, this is just going from one level to the other. When you would drop from the third to the second level in the hydrogen atom, okay, you will release energy that is visible light out there in the red part of the spectrum. That's 656 nanometers. Then a 4 to 2 jump would give you the 486. The 5 to 2 jump would give you the 434 nanometers. And only that specific amount of energy that corresponds to that specific wavelength, and that's why those colors were always the same. Now, this was an amazing idea, okay? And this was happening right about 1914. One of the big problems is that's also when World War I broke out. And physics research got put on the back burner, number one, because most of the people that did physics research were males, age, say, 18 to 40, and the first people to be drafted are males, say, age 18 to 40, back in World War I, okay? And also because if you were still doing physics research, it now needed to be part of the war effort. A lot of work at things like, aiming weapons, trajectories, and chemical warfare, and radar, things like that were becoming a really big deal. Okay, so now let's look at a little bit of math. Let's imagine an electron jumps from the n equal 3 to the n equal 2 level. What's the wavelength of the energy emitted? Well, we would use the Rydberg formula, and it would be 109,680 times 1/4 minus 1/9. See, it ends at the n equal 2. N final is 2. 2 squared is 4, so we have 1/4 minus, and it started at the n equal 3, n initial is 3, 3 squared is 9, so minus 1/9. And that's in centimeters to the minus 1, because that's not the wavelength, it's the 1 over the wavelength, so what we call the wave number. So that wave number is 1523 centimeters. Convert that to wavelength just by taking the reciprocal, and we get 6.56 times 10 to the negative 5th centimeters, which is 656 nanometers, which if you look back at those circles or at the spectrum on the page before, that's one of the lines in the bright line spectrum. Now, what about for the 4 to 2 jump? Do a very similar calculation, and we end up with 4.86 times 10 to the negative 5th centimeters, or what we would call 486 nanometers. All right, so this leaves us in a really great place in physics where we're about to have a really good understanding of the structure of the atom. And then we got this Serbian who takes a shot at Archduke Ferdinand, kills him, kills his wife, and World War I breaks out. So real solid research in the structure of the atom is not going to resume until after World War I. Okay. Thanks for tuning in. This is Morgan, signing off.